Okay, thank you very much. And thank you very much to the speakers for inviting me and for putting on this lovely little workshop. These kind of events are great. We haven't had so much of them obviously for a few years, and they're really the thing that keeps a field like this alive and generating new ideas. So thank you very much for doing that. I hope there'll be more of them. So I kind of want to talk about two things. I'm known for my work in non-smooth dynamics. I do stuff in singularities as well, and particularly over the last 10 years, I've been trying to understand particular singularities of non-smooth systems and how explain the existence of non-smoothness to some extent through what we call catastrophes. And it's more really just catastrophes and less non-smoothness in the non-smooth mechanics sense that I wanted to talk about today. But having watched a lot of your talks, seeing there's a new generation coming up through the ranks, and seeing that a lot of these systems are moving into higher dimensions and systems with large numbers of switches, large numbers of contacts and things like that going on, I felt it more important to talk about this bit, the second part of my talk first, so I've shuffled stuff around. It's kind of by accident been my job in non-smooth dynamics to show that there are certain circumstances in non-smooth systems that lead to indeterminacies, and not just indeterminacy, but uncertainty, sensitivity to conditions. Here's the basic fact. When you've got a non-smooth system, it's not differentiable. We know mathematics textbooks will tell us. If it's not differentiable, you can't guarantee uniqueness. In fact, the mathematics books will say, don't study these things. That's why I live in an engineering department, not a maths department. That's why in the 1980s, Teixeira had to call these things divergent diagrams because he couldn't study non-smooth systems. He'd been kicked out of his department. And we largely sweep that under the rug. So we take these non-smooth systems, we might smooth things out, we might simulate them in a computer. We're doing engineering type problems. We know they've got solutions. So we just assume we can do something with them. Those solutions will drop out. There are instances where those solutions will be complete nonsense. So I'm trying to bring that out. And there's a particular situation here, which is the one I'll describe, which is where you really have to be very careful. Mostly you get away with it, but you're only getting away with it. You're only being lucky. So let's get into it. I've tried to capture it because I've been trying to talk about this now for a few years. And struggling to get the message across. I've tried to capture it in a nice little thought experiment. So this thought experiment I call the pilot's dilemma. So I have two pilots on a spacecraft flying to Mars, one Mars, next target. And as we all know, when we watched Apollo 13, the ships always break, the electrics have gone down, and these pilots are left with just two thruster controls. One of them can control a pitch thruster, one can control a yaw thruster. And they're just going to fire puffs of this on-off control. And so 1-0 situation, so this will be pilot X or pilot 1 firing or not firing. This is the other pilot firing or not firing. And each time one fires the pitch thruster or the yaw thruster to try and control this thing onto a crosshair target to aim at Mars, that's going to have a little impact on their full direction as well. So fairly simple scenario. It's going to be fairly obvious they can control themselves onto that crosshairs, but it's the forward motion that's going to be interesting. My original version of this thought experiment was more like Schrodinger's cat, because this is kind of what's happening. You know Schrodinger's cat from quantum mechanics. Someone already mentioned quantum mechanics, so it's come up a couple of times, surprisingly. You've got a cat in a box, and there's a radioactive source which is going to break a vial of poison. And because of the probabilistic nature of quantum mechanics, you don't know whether the cat's alive or dead. And in quantum mechanics, the cat's both alive and dead. Well, in this version, you've got two people, or pilots, who for some reason are slightly sadistic, and they're controlling two valves on a tank. One lets poison into this tank, and one lets it out. And so they're just twiddling these in response to how much flow rate they've got at either one. You can imagine that as a more practical thing than torturing cats. And then Z is the amount of poison in here. And because of what I'm going to show you, you can't determine the amount of poison inside here. You can't figure out in this classical scenario, because of non-smooth dynamics, whether the cat's alive or dead. I printed out the original draft in our school office, and someone saw this picture and reported me because they thought I was proposing an experiment to torture cats. And I think 2020's sensibilities are a bit different to the 1930s. I decided that wasn't the way to go, so I came up with the pilot thing instead. All of that's all fun and games, but we are designing a robot experiment at the moment. We're starting to try and build these things to demonstrate this in real situations. So, and the simple scenario is you have two of these little guys, X and Y, robots facing off against each other or trying to follow each other, and deciding to speed up or slow down relative to each other, and some other guy making decisions based on them. And they can control their motion, but if he's making decisions based on theirs, based on the switches they're making, he's going to lose control. I'm going to show you why. And it's all capturing the worst form of indeterminacy that turns up in these systems. It's really simple. So, as I said, these guys are doing kind of an on-off thing. So in my state space, they can be both on, both off, or in a mixed states. And I'll drop these Boolean type variables into the right-hand side of an ODE to give me different vector fields on the right here. So if these are 1 and 1, then according to some functions, I'll have certain modes, certain speeds on my right. And so these things allow me to encode decisions into the right-hand side of this equation. So if X is high, I'll multiply something by lambda X. If X is low, to turn that switch off, I'll multiply by 1 minus lambda X, so that when lambda X is 1, this thing's 0. If I have something that depends on this mixed state, this double state, both X and Y being high, I want both switches on, that to have some impetus on the system, then I'll put in a multiplicative term like this. These were kind of inspired, they're not just pulled out of thin air. You see them a lot in genetic models and some neural models. So this is very much the kind of form you'll see in genetic regulatory networks, with some lambda X terms, lambda X times lambda Y terms. So this is what I use for this pilot model. So I'll do a bit of non-smooth dynamics. So here I have this typical trajectory. This thing's going to come in towards my X equals 0 threshold, and it's going to slide along that surface. And because I'm in 3 dimensions, so I've got one switching threshold at Y equals 0, one at X equals 0. And then if I come in and slide onto the crosshairs of that, I'm going to move along that Z axis. How fast am I going to move along that Z axis is the question. Should be pretty simple. But when you're dealing with differentiable systems, if you have a differentiable model, you have this expectation that it's robust, structurally stable to some extent. If you perturb it, it won't change a lot. If you perturb it order epsilon, the behavior will change order epsilon. If your real system lies a small distance from your model, the behavior will be similar. Not with non-smooth systems. This is our real problem that we have to tackle when we're using this model. So whenever I have this, really what I have is I'm modeling a system where I have some sort of dynamics at my switch. Right? We start off modeling these as Heavisides, but then one person will smooth them out, one person will so that we've always got some kind of layers in it around which we've got something else going on. We might have noise effects, we might have smoothing, we might have higher dimensional processes going on that regulate the switching. So these things in here could be smooth and nice and deterministic, but they could involve shattering and all sorts of other stuff. And this is where we're going to run into trouble. So as long as so this is my trajectory here running down one of the surfaces and simulated in a smooth system. This is one in a hysteretic system and other forms of non-ideality motivated by the various things you'll hear people talking about, the various things that people tend to use. So in physical compliance systems, we might use smoothing, or in neuron systems. In electronic systems, it tends to be hysteresis. And choose your area. Machine tooling, there's lots of time delay. As soon as you stick this thing in a computer, some form of discretizing, that turns out to be the most dangerous one, probably. And then noise and lots of things that Rachel will help us solve in the next few years, perhaps. So, none of this matters too much, right? I come in, I've dribbled down this surface, and Filipov dynamics tells us pretty much that you'll move down that at the Filipov sliding speed. But then you hit this little intersection. Let me blow that little intersection up there. Something's bouncing around inside there. So that's that little point there, blown up into a block. In my smooth system, I go to a simple equilibrium here. In my hysteretic system, I'm chattering around something hideously high period. My time delay system, I've got some other attractor. So no surprise that those different kinds of implementation, those different kinds of process are leading to different kinds of attractor. The problem is those things are really, really sensitive for one. So if I change my parameters slightly, so I've got a width here, an epsilon, a different epsilon here. If I change those slightly, I'll get completely different attractors in here. And this is similar to what Daniel was describing. For a hysteretic case, this is like a little billiard problem, something chattering around in here, and you get all these different kinds of billiard type orbits whizzing around. Change a parameter slightly, they change massively. The trouble is, it's these attractors that determine how long in each of these I'm spending in each of my modes. And that time I'm spending in those modes determines my Z motion. So you can see, for instance, in this one, I've got long time spent in the two modes where I'm traveling between the 1, 1 and the 0, 0, but the other two modes have only got tiny PC. Whereas in here, everything's a little bit more uniform. And it turns out that's really bad. We haven't understood all of that to a great extent, but we've started to make a few strides. I'll give you a bit of an intro into what we're doing to understand that more now. But first, the effect. So, as I say, the time I'm spending in my different modes as I'm bouncing between them determines what my Z motion will be. So here's the simulation I did for this pilot model. The green and red are the X and Y, the pitch and the yaw. So they're controlling that somewhere near onto the 0 surface, so it chatters around the 0. But when you just simulate the Z speed, well, if these guys are making their thrusts every second, perfectly every second, then I'll get some particular speed coming out of my Z motion. If one of them is always, I think it was 0.01 seconds ahead of the other one when they make their decisions, I get a completely different motion, which is almost no motion at all in the forward direction. If I switch it around, so the other pilot is now the one that's 0.01 seconds ahead, suddenly these guys are flying backwards. And these are simulations. So these are from a paper a couple of years ago. These I just did as I was preparing this. I thought, I'll let one pilot just make his decisions every second, but I'll make the other pilot make his decisions every 0.99 seconds. So he's not always proceeding and he starts lagging behind more and more. And as he lags behind more and more, the Z motion here goes absolutely crazy and variable. And choose a different initial condition and you see something completely different again. Hopefully you can see that green line. Badly formatted because I literally just did them at the beginning of this week. So, I mean, this doesn't look like a simple system. All I've got here is 4 constants. I've basically got 4 three-dimensional vector fields here, and I've stuck any constants in them, anything we like. And what I get out here does not look like constant motion, and it's just through a lack of simultaneity or a lack of perfection in how those decisions are being made. So any kind of system where you have 2 switches being made at the same time can have this kind of unpredictable knock-on effect on your system. We tried to understand what was going on from the point of view of Philipov dynamics for many years. This is a simple sort of, so I've changed my coordinates here, sorry to jump halfway between changing coordinates. So here I've got a simple, I'm just come in and I'm on this x equals 0 surface. So this is described by simple Philipov sliding. So this is just a simple system which switches between a mode A when x is negative, this is a heavy side, and a mode minus B when h is 1. But basically, it's just switching between something pointed that way and something pointed that way. And I'm not worrying about the other switch as well. You do your Philipov type analysis, and you'll find that x dots will be 0 when you're sliding. The y dot, you can work out what it is, and this is what comes out of the Philipov analysis. You put in any kind of perturbations, hysteresis, noise, any of those things I said, of size epsilon, and you get an error, which is a size epsilon over t, and t is your time of travel. So my error is just epsilon, and it actually shrinks the longer I go. So good, this is why it works. This is why we still have this. Otherwise, 100 years after this stuff started first appearing in the Russian literature, we wouldn't still be using it. But it's actually hiding something really complicated going on under the hood. This is the periodicity of that simple orbit chattering back and forth. What I've done here is I've discretized the system. So I've taken a time step of epsilon, And then I've introduced a time delay as I go across the switch of tau. And so as I change my B over A ratio, that's just something indicating the vector field. And I change my tau here. This is the periodicity of the trajectory going back and forth. So periodicity is a bit like the thing we've seen a few times this week. Oh, if I hop once on each side of the surface as I go across, I might call that a period one. If I hop twice on the right, and then once on the left, that's a different period. So you encode those periods. And they change massively. And the point is, if I let epsilon go to 0, let my time step be as small as I like, make the simulation infinitely good, make my system really ideal, none of that goes away. That's all just squashed up into an epsilon region. So no amount of precision will get rid of this massive uncertainty. That's always hiding there, lurking in that surface. You just don't see it because you don't care. It's squashed up in order epsilon. Now, we are never going to, in fact, it's held us back a long time, trying to understand what's going on by deriving the maps to get this kind of periodicity and study this analytic structure. And then my student, Sal Katsis, came along with a nice simple idea of simplifying this massively. And we really think this is, or I think this is the way forward for studying these problems. Is to think of this, instead of all this nice filibuster, just think of it as a Markov chain, a simple chain process. So I've got my 0 mode and one mode, my left and my right. And I'm either, in each second or each step, returning to 0, staying in the same mode, or moving to the other. And so I can then write down a transition probability matrix for whether I'm going to transition from one mode back to my itself, or transition to the opposite mode. And from that, you can write down the spectral gap of, well, I mean, you can evaluate that probability matrix in various ways, but this is its spectral gap plotted, and this reflects all of that uncertainty. I'll show you, you can't quite see it quite as well just yet, I'm going to show you it. But the real point of this is deriving, or this writing down, calculating this transition probability matrix doesn't care what kind of implementation you've got for the system. You can do it, whatever processes you've got going on with it. And so you're treating this really like a blind system. You're saying, look, it's really complicated. I'm just going to treat it as if it's stochastic because I really don't know what's going on. So if you look inside this, there's a lot of structure. I'm going to zoom in on a little bit, show you a bit more of the structure. You can maybe, depending how far back you are, see that there's all sorts of different colors, different values in this spectral gap, showing changes in these transition probabilities. So I'm going to zoom in a bit more. There's a little line in here where things look rather variable. And my student zoomed right in on this thing. And that is not numerical noise, that's not numerical artifact. That's genuinely the variability in this probability matrix of your transition probabilities for hopping back and forth across the surface. And I'll put the scale back on there so you can see it. That's a tiny, tiny space in your... So this thing's massively variable, and it will be any kind of implementation you put in. So when you've got switching in a system, this is happening underneath. And if you're smoothing out, you're just immediately washing that out. And anything else you're doing, you're picking out solutions from this very complex space. But who cares? It's all trapped within order epsilon, so nothing matters. Until I go to having my 2 switches or more. And the more switches you add, the worse it gets. So here's the problem. Don't worry too much about all this, but this is just writing a very similar system. A vector field where all the arrows point in nicely. I do a Filipov type analysis, which tells me, so I've got my x1 and x2 here. Those are going to stay within order epsilon of the crosshairs, of the switching surfaces. They have to. This other bit has some Filipov-like terms. It has this order epsilon over t term, but it has this guy here, this mu. And this mu is essentially measures the time proportions that you're in any one of your modes. And that remains completely undetermined in this state, written as a transition probability thing that already starts to look quite complicated, but it just means you can write down these two transition probabilities, calculate the spectral gap of that thing again. And it shows this massive variability. This one's less pretty than the last one, just because here I've got a time delay along one direction and a time delay along another. I've showed some other parameters. I'd see the same variability in maybe prettier pictures. But all that variability is still there and will remain as you let epsilon go to 0. And that matters because it's essentially this that determines mu. And if I just plotted, instead of the spectral gap, if I plotted mu here, you'd see the same thing. So any slight change in my implementation on how this is working, any slight distance between my model and reality, and this mu will vary enormously. It's not just indeterminate. A little tweak and it just will jump. It's highly sensitive. So that's the real problem. And as you go up, as you add more switches, you have more indeterminacy. You have more of these mu's appearing. So that's our problem for the next few years, is to really understand in more detail. We can see essentially that this thing turns up when you have the intersection of switches. And we want to understand more now using this kind of approach about how it turns up, when it turns up, what situations you really have to worry about this. But I wanted to highlight that at the beginning of my talk for anyone who goes studying systems that might have this sort of thing in. And yeah, so essentially, this thing creates all of this kind of uncertainty in your motion, this variability. You shouldn't take anything for granted. If you have behavior like this, at first, at least, you should try simulating it different ways, try running in different ways, perturbing it with different things. If you smooth it, try sticking in a bit of hysteresis, a bit of noise, something to test how robust your system is. In a way, a smooth system wouldn't really matter. So you have an indeterminacy, but not just, we've always known the indeterminacy, but it's not just that. Around these intersections, it becomes highly singular, and that creates an uncertainty. And the illusion, when you look at this, I mean, you think this system is noisy. There's no noise in that system. So it creates the illusion of noise in systems like this. In the book I wrote in 2018 already, there was a whole chapter called Illusions of Noise. There's all sorts of ways non-smooth systems can look noisy when there's just no noise in them. There's just what I call hidden dynamics, hidden complications stuck inside the switching circuits. But when you perturb them, when you look at a more realistic, less idealized way of simulating or analyzing them, is all unleashed. Okay, so that's kind of doom and gloom, but if you don't run into that scenario, then you're okay, mostly. It can happen on a single switching threshold, but it's rarer. So the other thing I want to show you is more of a useful thing. It's a little cheeky. It's not really non-smooth dynamics, but 60, 70 years ago, when people would talk about discontinuities, they weren't talking about the non-smooth dynamics we're thinking about. They were talking about bifurcations, or the precursors to bifurcations, catastrophes. And we use these things all the time. So we take our ODEs or our PDEs or whatever we're looking at, and we study with auto and matplots and using the Abbotsford and nice bits of software, saddle node bifurcations and cusp bifurcations. And those go on and on and on. Anyone know what, so if a saddle node is 2 equilibria crashing together, a cusp is 3 coming together. Anyone know what's after that? 4 equilibria crashing together? You want to give me just some idea of who I'm talking to? No? That's good. And so that lots of work was done extending that classification, but around the 70s, they kind of lost interest in doing that. In fact, they classified it completely to death to infinity and moved on to things that evolved over clinics and limit cycles, got distracted by Bogdana Tarkins and Hop and double hops and all of this. But so recently I was brought this problem. So we've seen a few of these this week. Nice bifurcation diagram. These black lines here are folds or saddle nodes, where my number of equilibria in my system of steady state changes. In this particular system, I was brought by a couple of colleagues, Alan Champnis and Fahad Al-Sadi. This comes from a 4-dimensional PDE, and essentially, the things plotted here are heteroclinic connections between steady states of the system. So these are spatial states that travel between one steady state of the system and another, that give you a wave pinning phenomenon. I'm not bothered about any of that. I'm interested just in the steady states. So the steady states of this thing can come together and collide, and if they've collided and disappeared in a saddle node, then you can't have any heteroclinics. So just by studying the steady states, you can find out about a lot about when these things that they're interested in exist. So we have all these black lines that are folds. These other colors are the heteroclinic connections and things that exist. But these folds can pinch up along cusps. So those things are cusps. You might recognize those from your own bifurcation plots. But they notice as they change parameters, those cusps could, this whole picture, in fact, could sort of come in and collide and crash together in a. No, you really don't know, that's good. So in what's called swallowtail bifurcation. So two cusps come together, they make a swallowtail, where four equilibria can collide. And these are more well known from physics, which is where my background was in geometrical optics. I was going to find a second. So these are images of light diffracted off a plastic film, and they behave a bit like these bifurcation plots. Just as my number of equilibria in the system changes as I go across a fold, in these, the number of wave solutions you have to a problem change as you go across these bright acoustics. And that's what creates, they're not really clear on here, but so for instance, in the center here, you have four wave states and they create the nice bright diffraction patterns in this period you go across. And those folds, by the way, are the same kind of fold that create a rainbow. You could see them more easily. I've gone around showing people last night at dinner if the light conditions were right, but the light conditions have to be good. You'll often see these things. You'll hopefully recognize this one. You'll have seen this on your coffee cup on a sunny day and on your beer mug. This is off the bottom of a wine glass. And in my day, we had these things called OHPs, where a light would shine up from below. And if you stuck a wine glass on this thing, then you'd be able to see really beautifully those kind of patterns. And it's, I don't think of one actually. So I'm not really going to be able to show you this very well because it doesn't work like it did on the old OHPs. So I was playing with this, and about the best I can do. No, I wouldn't even bother to do that. That's fine because I'm not really. I can see it. Here, come here. You see those patterns there?
Yeah.
Tell everyone they're beautiful, aren't they? So you can almost see them, and if you can see them really clearly, they're really good because they're nice to try it when you're next time you're sitting at a dinner table. People hate getting stuck at a dinner table with me. I start explaining catastrophe theory to them. Yeah, sort me out. The great thing is as you tilt your wine glass, you'll see these patterns change. And what you're doing is exploring a high-dimensional catastrophe surface. You're watching bifurcations unfold as it happens. Or if you stand and watch a swimming pool, you'll see those kind of patterns going around. And you're watching catastrophes being unfolded before your eyes. And these are the surfaces. These were what were described by Tom, René Tom, around the 50s, 60s. Simple monomials with more and more turning points. And as you unfold them in the space of these parameters, they make these nice characteristic surfaces of a simple fold. The fold is literally just a fold. A cusp is just a cusp where those folds form up into a cusp shape. And then you go higher into the swallowtail and butterfly. And it's that swallowtail shape that my colleagues have noticed in bifurcation. But the catastrophes only describe either one-dimensional problems or scalar functions. They only work for scalar functions, but those can be extended up to any order. And you can go up to any polynomial order, any number of parameters, and easily describe those and find them, just finding the turning points of functions. In our bifurcation diagram, we've got not turning points of a 1D function, but steady states of a vector field coming together and colliding. How do you find the same things? Well, before I do that, once Tom had shown these lovely surfaces, way back when, drawing them by hand, there weren't computers that could do this sort of thing, people went a bit catastrophe mad for a little while, and they're not really stopped. They love a good cusp. These are just a few. Type cusp into Google, and it'll explain to you whether you should be investing, whether you're going to lose your job, whether your marriage is going to last, whether your Tinder date's going to work out, everything. The area fell into disrepute a bit. Actually, look, people don't even change the surface when they do it, not even rejection. So it only got a bit crazy. But we use this stuff now. We use it routinely in these sort of things. We know we study folds and cusps, but we don't really go beyond that. We don't go beyond that because you can't. If you've got, and contradict me if I'm wrong, your continuation software can find folds, it can find cusps, and then it can do some hop and double hop and stuff like that, but nothing beyond that. So if you think you've got one of these higher code dimension things going on, how do you find it? That's what Fathead and Alan came to me. And I didn't know, and I couldn't find one, so I came up with one, which is what I want to show you. It's beautiful simple. First, to show you what you should do according to the textbooks, then learn it. You should, to show that you have a certain kind of bifurcation, make a center manifold reduction to find the local form around your bifurcation. Right? Local to what? I don't know where this thing is in space, let alone how hard it is to do center manifold reduction and change coordinates. Lots of technical stuff, but it's not going to solve the problem. Basically, textbooks aren't going to allow you to find these points where a swallowtail exists in space. To my surprise, after it solved, came up with a beautiful, simple solution. I was like, they must have done this for the last 60 years. These guys were so amazing. They did such great stuff. They must have known the solution. They had a solution. So after Tom had classified everything, this guy Boardman came along and algorithmatized it into this. I mean, you see how simple and beautiful this is. So you're quickly writing this down because you're going to use it later. For any singularity, there's a sequence you can build up which will classify any singularity bifurcation of a mapping, a function f, from any Rn to Rn. And it goes like this. Ready? I'm only going to explain this quickly. Have I got? Am I supposed to finish at 5 plants?
It's fine. We start with it.
You don't really want to know this, so this is just to give you an idea of what it is. So I take my function, in which I think I've got one of these high codimension things. By the way, I should show this because I don't think anyone, even in my area, knows this classification exists. It's just disappeared. But it's so general, that everyone should at least know it's there. You take your function, and then you put that function with all of those components, and you take its determinant, its Jacobian. Now you know that if the determinant of the Jacobian vanishes, you've got a bifurcation. To do it more generally, you want a slightly more general object. You can think of that as the n by n minor of the determinant, which is a trivial state, that just means it's itself. But you can take all of the minors of that Jacobian determinant, of the Jacobian, the minor matrices, so the small sub matrices, right? So I take my F and I put all of those minors into an object. And then I do that again. Now I take the Jacobian of that big thing and call it this object, and I'm going to drop that in there. And I'm going to take all of the minors of that object. And then I'm going to take all of that and take its Jacobian and find all of its minors. And I go on and on and on doing that. But if I look at all of these matrices and I find that they're full rank, so if there's singularities, the bifurcations, they won't be full rank, they'll be slightly less. So you find how much less they are. Write down all those numbers for all of these. And you've got a classification of every possible singularity you can have. It's wonderful. Almost. How many calculations is that? Quite a lot. It's a sum at each level. So each of those steps is one of these J's. It's a sum over products of binomial coefficients of the sum of all the previous ones. If you know how factorials work, you have an idea that's going to be a big number. I love these numbers. This is how many calculations it's going to take you to find and classify your singularity. So here's my dimension. So remember, for the system I was looking at, I had dimension 4. This is my codimension, the number of parameters of the system, if you like. So a fold, not too bad. A cusp. Now already for a cusp in 4 dimensions, I'm claiming I've got to solve 10 equations. If you know codimensions, you know that's too many. I've got 4 dimensions, so that's 4 of my things. I've then got 6 more equations to solve for a cusp. Well, a cusp only has 2 parameters. So how am I going to solve 6 equations? For the swallowtail, 220. So these guys thought they had a swallowtail. So if I was using this, I'd be trying to solve 220 equations. It wasn't a swallowtail. It was a butterfly. For that, I solved 95 million equations. I do stuff by hand. I didn't solve 95 million equations. I wanted something a bit simpler. The other problem with this is it does, the sneaky thing I put in there was it goes for any function from a space Rn to a space Rn, but that's just a mapping. That's not a vector field. It has no notion of directionality. So it doesn't know about stability. So we'll ignore things like limit cycles and home clinics and stuff like that. So to classify a proper bifurcation of a vector field, you need even more conditions. So the conditions just don't exist, but they should do. So I'll show you what they are on the next. But this is how many it reduces to, the absolute bare minimum number of conditions you need which is the dimension of your space plus the number of parameters it can solve for. And it works for vector fields. You say it works, it doesn't care if it's a vector field. This is going to work whatever you've got. And it's done by reducing the problem of looking for a strict bifurcation to looking for a catastrophe. And I call them the underlying catastrophe of a bifurcation. And it really just looks for detecting where equilibria smash into each other. And these are all the conditions you have to solve. So as codimension R, I have to solve for where these BJs from B1 to BR vanish. And these are simple determinants, so they're pretty easy to calculate. The first one is just the Jacobian. And then I take the determinant of the Jacobian and I drop that into the first component in place of one of my components, my F1. And I take the determinant of that, and I get the next symbol. And I take that symbol, I drop it back into the first component, take the determinant. Essentially, they're quite simple. There are some other, whenever you calculate these things, there are non-degeneracy conditions. You have to make sure it's not degenerate. Turns out there's quite a lot of those. They're a bit nasty. There's no magic in mathematics. All of those many millions of conditions in Tom Boardman had to go somewhere. And they go into these non-degeneracy conditions. But then non-degeneracy conditions, all you have to do is calculate them. You haven't got to solve them. You just do a simple calculation to check them on zero. So that's straightforward, no problem at all. And it just checks that everything's nice and solvable. So you've just got this simple set of minimal conditions to calculate anything. So this sort of stuff could just be built into auto and all these, HubSpot and all of these, to solve higher codimension things. So as I say, I call them the underlying catastrophe of the bifurcation. You don't fully classify the bifurcation, but once you've found it, you can do a full analysis. It's appropriate to call them an underlying catastrophe because, in principle at least, you could do a reduction on that thing, put it into a normal form, or what Arnold calls the principal family, and inside that, embedded inside your vector field, are just Tom's elementary catastrophes. So it's all, I think, kind of cool. So this is a thing that isn't strictly non-smooth, apart from being, if I'm selling catastrophes as non-smooth. So, but this should work. But smooth systems, non-smooth systems. I figured it was worth showing to people anyway. Now, this is the explanation of why it works. And there's some beautiful geometry in there that goes back to stuff that Tom and Whitney did. There's one thing I've understood over my career is that people don't like philosophy and maths papers. That wasn't maybe too surprising. More surprising has been people don't really like geometry. So sometimes I lecture about all of this stuff and how this works, but people really don't like too much geometry. And Tom found this as well. After he'd come up with his catastrophes and released them on the world, he just couldn't cope with. People didn't like qualitative stuff, and they didn't like geometry. So he left and left mathematics and went into philosophy entirely, which I may well be doing soon. And there's Tom riding down the Amazon, I believe, on a boat with my old PhD supervisor. Had quite a line around and no idea where it came from. So I'll only whiz through this. This is just to show you the high codimension things. People are scared of high codimension, they're hard to find, they don't appear, they're hard to calculate. With these conditions, on the problem I was given, you can do these things by hand. So I did this on a little A5 envelope at first. And this was the calculation up to a codimension or butterfly, and up to a codimension 6 as well. You can do quite a lot of this by hand. The rest of the computer will do for you. And they give you different kinds of behaviors. So it's not just about being able to find high codimension stuff. These are two systems which both have 4 equilibria, which are going to collide in a catastrophe. They're slightly different, but the way they're going to collide is going to be different. There are my conditions to work out a swallowtail. This is what I'm working on at the moment. There's another class of catastrophes called umbilicus. These are a bit tougher, but what you really see when you're looking through a wine glass, you see umbilicus unfolding. You want to satisfy slightly different conditions. And in these, both of them involve 4 equilibria colliding. So here, the 4 equilibria are sat right on top of each other in a planar vector field. So the red and the blue are the null lines of those of the vector field. As they perturb, you can have no equilibria, or 2, or 4. And it's those 4 I just briefly want to show you. If they appear from a swallowtail, you'll have 2 saddles in here and 2 nodes with the same stability. So they might both be unstable or both stable, but they've got the same stability. Whereas in the umbilic, it's quite different. you'll have again two saddles, but you'll have two nodes of opposite stability. So being able to classify these things is quite important for the state of the system, especially if these are involved in phase formation, things in crystallization. And the other important thing is there's two different forms. This has 3 parameters and this has 4. So for what looks like the same bifurcation, they have them quite differently and they have different numbers of parameters, different code functions. The other, pretty much now, the other interesting thing I'm just beginning to look at is what happens when you've got these in a reaction diffusion. So in these kind of PDEs, and you stick them into reaction diffusion equations and look at pattern formation around these catastrophes. If you're close to a catastrophe and you perturb a point a little bit, your equilibria are going to lose stability in something like a Turing bifurcation. And if you look around these catastrophes, you get interesting kind of patterns. There's going to be a lot of heavy analysis to do understanding what goes on with those. But the really nice thing is, it sort of brings together this stuff that Tom was doing, starting back in the 50s, with the stuff that Alan Turing was doing about the, sorry, other Alan Turing, was doing about the same time. These guys were both really motivated by the same problems of morphogenesis, so shape and pattern formation in living creatures. And they went at it from two very different angles. And bringing these two together would really sort of bring the two after 70 years apart back together. And that's kind of it. So, so I'm really kind of hoping that this will start to unlock a use of high codimension bifurcation theory, but more of a use of this catastrophe theory that's been sitting around a little neglected for a while. And this pilot's dilemma and the other problems around it, I think are going to unlock a lot of horror in the next few years as we really start to understand systems with multiple switches. But I think the way to go about it is study them as if they were stochastic systems. Well, if I can attract certain people's interest, then they might be able to get something. But thank you very much, and thank you to our organisers.